And so I'm going to share just the OLEX program folder to kind of give you an idea of where the ShellX programs need to be for it to be read by OLEX. And so here I've installed the OLEX 2.2-1.3. And when you install this program, it generates this folder OLEX 2-1.3. And when you download the ShellX package, the ShellX package just contains a bunch of executables of different ShellX programs. And what you do is you copy and paste those ShellX programs into the same folder that's titled OLEX 2-1.3. And that way, OLEX will recognize that you have those ShellX programs available. Likewise, with Platin, once you've copied that folder that I've put on Blackboard for Platin, you take you copy the pwt.exe, you post it in OLEX, and then OLEX will recognize that Platin is available. And so this is how you can have ShellX and Platin run through OLEX. And again, OLEX is a GUI that interfaces with these different programs. So that's the OLEX folder. And just to explain you a little bit about the different files that we have. So I'm in my Inclass structure 1 folder. So the HKL file contains the Miller indices, their intensity, and their error, just like we saw yesterday when we looked at a sample. The INS file is like an instructional file. When you first get one, it mainly just contains the lattice parameters, the symmetry type, a possible space group, and formula. So that's all it really contains initially. And then the P4P is another type of parameter file that contains machine constant lattice parameters as well. And so it's good to, when you're solving the structure of a crystal, to have all these different files, because what OLEX does is when you're finalizing your structure, it actually looks for all these different trivial bits of information from these files, so you don't have to enter them in by hand. So what we're going to do is, when you go to your OLEX program, when it opens up, you're going to open up the AMP_1-.ins file. And it's going to look something like this. I think this is it. Yeah. So when you open it up, it's going to say the AMP_1. It's going to give you, now this is just a possible space group. So based maybe from the machine when you were doing the integration or whatnot and the scaling and merging, it predicted P212121. This is just a starting point. So that's what that shows. And D min is the minimum D spacing. This was done in molybdenum radiation. I over sigma tells you the quality of the data. So again, you want an I over sigma of 10 or better. Rint, we talked about that yesterday, is the comparison of the symmetry related reflections. 1.3% is excellent. Completeness, usually you want it around 99%. If your completeness deviates a lot from 99%, you'll have to do some explanation, or you may have to collect additional data to resolve the completeness. And this is just like a Christmas tree. So whenever you see things light up in green, that means they're good. Light green is okay. Well, actually, I say dark green is perfect. Light green is good. Orange is okay. Orange or yellow. Red is not good. So if you have something with a red, that's a serious problem in your structure. So right now they're all green. Here we have the lattice parameters. The Z is the number of symmetry related entities. Z prime is the asymmetric unit. So here Z prime is 1, indicating that there's one molecule per an asymmetric unit. and there's 4 symmetry operators, so there's a total of 4 molecules in the unit cell. So the Z prime is the asymmetric unit. It tells you how many entities are in the asymmetric unit. It could be a half a molecule, it could be a whole molecule, it could be 2 molecules. It just depends on the crystal. Z is related by the symmetry operation. So since Z prime is 1, P212121 has 4 symmetry operators, so 4 times 1 gives us 4. Now, for example, Z prime was a half times 4 is 2, so then Z would be 2. So Z tells you the number of entities in the unit cell. So you would take the Z prime multiplied by the number of symmetry operators for that space group, and you would get Z. Now up here you notice the chemical formula. It says C5H6N2. Whenever you see this kind of orange arrows here next to the formula, that means you can click on it. Don't do it now, but you can click on it and it'll update the formula. So you always want to watch out for this. So whenever you make changes, you'll see that this will update, and you just click on this orange circle and it'll update the chemical formula for you. So over here, if you have platinum attached, you'll see this little icon here, P ton, which stands for platinum. So that means that OLEX recognizes that you have platinum linked with OLEX. But if you don't, you can still use platinum separately and then import the files. That's kind of just a brief overview of all the different functions for right now. So the first thing you want to do is when you open up and you're ready to solve a crystal structure is you want to click on the solve arrow, and the solve arrow gives you the program, the method, the reflection file, its composition, Z and Z prime, the space group. And if you're not happy with the space group selection, you can click on this which says suggest space group, and it'll see if it finds anything better. It should. Did it? Yes. And so here it only suggests P212121. There's no centrosymmetric space group present. Yes. So now you've selected the space group, but you can always, use what the machine software predicts, or you can come here and click suggest space group. Now, once you've picked the appropriate space group, you can change the different programs to do your initial solving of the structure. So the most common structure solution program is ShellXT. And ShellXT, what it does is it gives you an initial starting point to produce your structure solution. And the cool thing about ShellXT is that it also does a relatively good job at assigning atom types at the same time. Now, ShellXD is an older form of ShellX, which deals with very large molecules, or if you're dealing with something that's like a protein or something, you would use ShellXD. So you don't, for small molecules, we really don't touch ShellXD program. Now the difference between ShellXS and ShellXT is ShellXS is not automated in identifying the atom types, and so ShellXS is actually an old school version that you'd have to go in and label all the electron density peaks as atom types. And I'll show you both ShellXT and ShellXS and the difference between the two. And then OLEX has its own structure solution program, but I find that ShellXT is the most robust structure solution program, so that's the one I use on a routine basis. The method is just intrinsic phasing, so that's just a method to use to get you an initial starting point for a model of your crystal structure. And then after that, we're going to go to the refine button. So the first thing you should do is select the appropriate program. Make sure you have the selected appropriate space group that you want to use. And then you click solve. And hopefully if we did it right, it should solve the structure. And yes, now it's solving the structure. And so once it solves, since it's shell XT, it automatically assigns atom types based on their electron density. And this is our initial starting point for this crystal structure. I'm just going to open the chat and just make sure if you could just give me like an okay that everyone's gotten to at least this part in the process. Now, if you don't have ShellX, you can just use OLEX as well and follow along until you get ShellX installed.
Quick question. My structure loaded, but it's huge. Is there a way to make it smaller?
Yeah, so what you do is if you hold the right mouse key and you can zoom in and out like this.
Okay, thank you.
You're welcome. And then if you hold the left mouse key, you can rotate it like that. So right mouse key zooms in and out. Now on a laptop, if you're using the pad, it's a little bit tricky, but if you have an actual mouse, it works a little bit better. And then the left one rotates the molecule. So I assume everyone's good up to this point. So now what you want to, oh, one more. Okay, let's see. Chat. Structure isn't rendering. What is the error message that it gives? Error 3. We'll take a Max. We'll take a look at it at the end of class, and then we can look at it a little bit more one-on-one that way. Is that okay? Okay. So once you do the initial solve, what you want to look for is that everything was identified correctly, like the correct atom type. So this is where you need to know something about what you're solving. So you got to know the connectivity, what atoms are present. And so this structure here is aminopyridine. So aminopyridine means it has to have a nitrogen here and a nitrogen here. So this is where you have to look and make sure you have the correct atom types assigned. And if there was an atom type that was mislabeled, you would be able to pick it up. So for example, if I change this nitrogen to an oxygen, and let me just show you what it looks like. And so here, if your initial structure gave you something like this, then you may have to come in and say, well, this shouldn't be an oxygen here. This should be a nitrogen. And so what you do is if you right click on the atom, you go to type, you can select any one of these and change the atom type, or if it's not listed, you can go to more and select from the periodic table. So if you know that's supposed to be a nitrogen, you can change it to a nitrogen. And by the way, when using OLEX, there's like 3 different ways to do everything. So if you find a different way and it does the same thing, no problem with that. So now if we go to view, you go to quick drawing styles, if you pick ellipsoids, this shows you what the actual vibration of each atom looks like. And so right now they look like circles because what we have so far is we have isotropic thermal parameters. So let me show you what that means. So isotropic thermal parameters means that atoms are treated like spheres. So that means there's a uniform region of electron density around each atom. But that's not very accurate in modeling the electron density around the atoms. What's more accurate is something called anisotropic thermal parameters. Here, atoms are treated as ellipsoids. And so this does a better modeling of the thermal or of the electron density around an atom because it treats it more as an ellipsoid, because not all atoms display spherical electron density around it. And so that's why we do it. We run experiments at cold temp so that it minimizes the vibration of the atoms, so we don't have these elongated ellipsoids. So the way that we change this from isotropic to anisotropic thermal parameters is up here under model. You go ANIS all. Now, before I do this, let's explain a few things. So anisotropic is only for non-hydrogen atoms. You'll never give anisotropic thermal parameters to hydrogens. So hydrogens are always isotropic, they're not anisotropic. So this only is for non-hydrogen atoms. And you should most of the time do this step once you feel that you've correctly identified all the non-hydrogen atom types in the molecule or in the asymmetric unit. So once you think, hey, I've done everything correct as far as atom type assignment, then you come here and you click anisotropic all, and it's going to convert these to ellipsoids. And the way you know they're ellipsoids is you see these little hash or these little kind of lines on the atom. So these mean that they're ellipsoids now. You see they look a little bit different than the isotropic spheres. Now there's not much vibration in these atoms because these all sit in a aromatic ring, and remember this ring is very constrained, doesn't give a lot of freedom of movement for these atoms. So it's not surprising that there's very little vibration or elongation of these ellipsoids around the ring. Just another tip here that I can kind of show you to see if you've mislabeled an atom. So let's say, for example, this nitrogen here, we're going to change it to a, let's just for fun, we'll change it to a sulfur. And I'll show you how this ellipsoid will look distorted compared to the rest of the ellipsoid. So here we click refine. And you'll notice how this atom, we labeled it as a sulfur, or it was labeled as a sulfur. And you see it's very large. And now all the other carbon and nitrogen ellipsoids are very small. Because what's happening is this sulfur is so large it is sucking all the electron density. And so this is an indication that you have an atom type assigned here that's too large. So this would be a flag saying, hey, this might not be a sulfur here. It must be something smaller, because the ellipsoid is so large that it's making all the other ellipsoids tiny. So this is a wrong atom assignment here. So let's convert it back to a nitrogen, or we'll do oxygen, and we hit refine. Oh snap, I forgot to tell you about refine. Yes, so for refine, the best program to use is ShellXT. Oh, not this one. Let's go refine. My bad. I forgot to show you refine. Yes. So for refine, the best program is ShellXL. There's also an OLEX version. The cycles, it's a number of cycles it runs through to minimize or to converge the structure. And that's determined by the shift parameter. So the shift parameter tells you if the structure has converged, or are there still atoms that are moving around too much for it to converge. The peaks are the number of additional electron density peaks that pop up. Those are those brown spheres here. The HKA file we don't change. You don't worry about the weighting file, the weighting parameters now that comes at the end. And the other thing is make sure that this says ACTA, because this will write your crystallographic information file. So again, for refining, we use shell XL. If you're using OLEX, you can do OLEX2.refine. The cycles is the number of times it cycles through to converge the model, and that's based on the shift. So if you keep on seeing this shift parameter doesn't converge, doesn't go green, you got to keep on running the refinement until it goes green. Now, if it never goes green, that should be an indication that there's something wrong with your structure. So you got to investigate the structure. So right now we had this as sulfur. Sulfur is not right. That's why the shift parameter is not converging to 0. The number of peaks are the number of additional electron density peaks that are shown up after you've assigned the atom types. So these are other residual electron density around the molecule. So now I've changed this to oxygen, and every time you make a change, it's always good to refine until it converges. So if we hit refine here, so notice that when we change this from an oxygen, from a sulfur to an oxygen, our shift parameter went from 3 to 0.087. So that means we've changed the atom type to something better. Now, since it's still red, we can click refine again, and it'll converge to close to 0. So now it's converged. So you may say, well, why does oxygen work here as well as nitrogen? And we're going to show you how you can distinguish between oxygen and nitrogen in just a moment. So right now, everything looks good. We have a lot of green. So, you know, the I over sigma Rn is still good. Completeness, not bad. Shift is green. The goof, we'll get to later on. The flak parameter, for this structure, since it was collected in molybdenum radiation, it contains light atoms. It's kind of ambiguous. You don't have to worry about that right now. So the two things you want to look at are the R1 and the weighted R2. And so you've noticed that these have been turning from red to green. And so R1 is the comparison of the calculated structure factors from our model and the observed structure factors from the experiment, the data collection. And so the better that these two fit, the lower the R value is. The same thing for WR2. You have the calculated weighted structure factors and the observed, and now we use a weight there and we compare them, and the lower it is, the better the model is to the experimental data. So that's all we're doing with R1 and R2 is we're taking our model that we've made, we're calculating the structure factors, we're comparing them to the observed structure factors and how well they fit. So right now we're at about 8% R1 and WR2 is about 25%. Not bad, we still got a few tricks to do. So again, the only difference between R1 and R2 is that with R2 they use a weighting scheme to compare the observed and calculated data. So now if you see this orange circle here, you can click on it and it'll change your chemical formula to what is shown currently. So what have we done? We've solved the structure. Once we confirm that all the atom types are at least correct, then we do anisotropic refinement. So we change the spheres into ellipsoids. Now that we've done that, the next stage is to add hydrogens. And so for carbons, usually what we do is we calculate hydrogens based on calculated positions based on the carbons or oxygens that it attaches to. So there's many different ways to do this, but if you come down here, if you're under the refine menu, there's something that says toolbox work. And if you click on add hydrogens, this is going to add calculated hydrogens to any carbon, oxygen, nitrogen, or sulfur, whatever you have, if it feels that it should have a hydrogen. So if you click on this, now it's going to refine it automatically. So it's automatically calculated the hydrogens, put them in. So you'll see now that these carbons are sp2 hybridized, so they only need one carbon, one hydrogen. So you have to kind of confirm that there's the correct number of hydrogens. So again, each carbon is sp2 hybridized, so they should have one hydrogen. That's good. Now over here on the oxygen, you see it placed one hydrogen because remember oxygen, OH. But you'll notice that right here, we have an additional electron density peak that is close to the oxygen. So this must be something important here because it's very close to the oxygen atom. And so if we come and we right click on it and click bang, it tells us it's only about 0.84 angstroms from oxygen. And so a typical hydrogen covalent bond is anywhere from about 0.8 to 0.95 angstroms. So this tells you that, hey, this Q2 should be a hydrogen. And so, but we know that oxygen can't have 3 bonds, then it becomes cationic. So maybe we've mislabeled this oxygen, and maybe it should be a nitrogen. So then we change it to nitrogen because nitrogen can have 3 covalent bonds and still be neutral. And so now if we go back to add hydrogens, let's see if it adds it. No, it didn't. So it didn't add it, but let's say we delete this. Now we go to add hydrogens. You see now that it added 2 hydrogens to it. But our shift parameter is still not green, so let's refine again. And so the problem is that this hydrogen here is pointing up and it should be pointing this way. So now I'm going to show you a cool trick. So you watch this. This is pretty cool here. So we go to Tools and we go to Disorder. And we're going to select our hydrogen atom and we're going to click MFit. And what you can do now is you can move the hydrogen atom to fit it where you want. So we want it at this electron density peak. There. And now we hit escape and it's moved it to that electron density peak. And there's another way you can do it as well. I'll show you that. There's different ways. So now if we go back and refine, now we have it in the correct position. Now, if you're unsure, or that's a little bit of an advanced technique. If you're unsure, what you can do is if you delete all the hydrogens around the nitrogen and click refine, you see here these 2 electron density peaks resemble the hydrogens. So if you right click, go to type, put hydrogen, you can do it this way as well. So this is called determining hydrogen atoms from electron density peak. The other way is based on calculated positions. So whenever you identify a hydrogen from an electron density peak, you would say that these hydrogens were determined by electron density map versus the other ones which were determined by calculation. So now if you do assign hydrogens through electron density map, there's another important thing that you need to do. And if you right click on the hydrogen atom, you go to what's called UISO. We'll do that after we refine. So we hit refine. And then if you right click on those hydrogen atoms, you go to UISO, you select 1.2x. So any hydrogen attached to a nitrogen or a sp2 carbon, if you do it manually like we did, it has to be assigned 1.2x. If it's a methyl hydrogen that you assign manually or a hydroxyl, it has to be 1.5x. So you just click 1.2 and do them for both hydrogens. The reason you only have to do it when you're manually doing it is because it automatically does it for calculated. So you see the calculated ones, it already sets it to 1.2. So again, carbons that are sp, sp2, and nitrogen, they get the hydrogen set to 1.2x under the UISO menu. If it's oxygen, hydroxyl, or methyl hydrogen that you determine manually, it gets to 1.5x. So now if we go and redo our formula, and we hit refine, so any questions so far? I'll pause here if you have a question you would like to ask. Okay. So what have we done so far? We've solved the initial structure. We've correctly identified all the atom types. We converted thermal parameters to anisotropic. We've identified all the hydrogen positions. The rest of the work that we do is going to be more of technical things to look at. So typically with molybdenum radiation, the 2 theta cutoff, if you remember from our lecture the other day, the 2 theta cutoff is 50 degrees. So your data, your high angle data should go up to at least 50 degrees 2 theta. And so what we can do is if you click on this percent sign here, oh wait, yes. You click on the percent sign next to R1, it's going to show you how your data looks. And so what you're looking for is you're looking for a linear trend in the data. So if you saw some outliers like up here or up here, we could remove that data. Now 50 degrees 2 theta is right about here. So we need at least up to 50 degrees. The rest of the data, I mean, it's good to have more high angle data, but if you wanted to omit, say we wanted to omit at, so this is 50, and this is 55. Let's say we want to omit all data above 55 degrees 2 theta. So what we would do is we would go to edit, instructions, And just somewhere below where it says LS, just make a new line and you'll type omit -355. And what this does is this omits all high angle data above 55 degrees to theta. So you hit OK, and you're going to see our R factor increase. And so by omitting the data above 55 degrees to theta, you see that our R values became significantly better. Because remember that high angle data is usually weakly diffracting. It may not be very good data. So it's okay if you remove it. 55 is a good benchmark, but the lowest you can go is 50. If you go below 50, you're going to have issues explaining why you went below 50. Secondly, what you can do in regards to data, if you click on the info and you go to bad reflections, here it will tell you if you could omit any reflections. It would say in red, oh, you can omit this reflection. So here's also where you can omit certain reflections as well. Just to show you what it would look like, let's say we set this to 3. I won't do it, but it would say in red, it would say omit here, and you can click on it. So, but no, all of our reflections are fairly good, so we're okay on that part. The last thing we need to do is what's the weighting parameter. So the weighting parameter is to help with the reflections, because not all reflections are created equal. So the first weighting parameter, what you're going to see there is it's going to lower the R2. The second weighting parameter, it's going to adjust the goof. And the goof is the goodness of fit, which you want around 1.0. So what you can do is if you want to use the OLEX determine weighting parameters, you can just click on them and then hit refine. You're going to see the R2 decrease a little bit, and then the goof adjusts accordingly. So you saw the R2 decrease, the goof increased a little bit. So typically what you want to do, the first weighting parameter, it becomes smaller. The second weighting parameter goes larger to adjust respectively the WR2 and the goof. So if you decrease the first weighting parameter, it's going to decrease R2, but it's also in turn going to increase goof. The second weighting parameter, when you increase it, it decreases R2, so there's kind of a balance between the two weighting parameters. And if your second weighting parameter is above 5, you'll start to get some errors showing up, because that tells you there's something wrong with the structure, the model you're using. So then you can click on it again, hit refine, and now it doesn't really suggest any more changes with it. And another thing you can do is if you want to get rid of these brown spots, if you just roll the mouse down, it gets rid of them. You roll the mouse up, they come back. You roll them down, they disappear, come back, disappear, come back, disappear. So again, you roll it down, they disappear. You roll it up, they reemerge. So as far as structure solution, this is pretty much the finish line. Now to get it ready for publication, what you would do is you would click on the report button here. And here's where you would enter information about your crystal. What's the color? What's the size? So this is what is measured. So I'll just put some values here. And then the shape of the crystal, This one was a plate. How was it mounted? This one was mounted with what's called a glass fiber. So this is things you know from the data collection. Now, a lot of this is auto incorporated when you have modern or using newer versions of software. But like for diffraction temperature, you would put, this was 98 Kelvin, and cell temperature 98 Kelvin. So these are all things that most of the time they're there, but sometimes they forget to add them. This, you can come in and add them here. Now, since this is in a non-central symmetric space group, it wants to say that this is the absolute structure, but since we did this with molybdenum, and these are all light atoms, there can't be any relevant absolute structure information, so you would set this to not applicable, because with molybdenum radiation, you can't determine the absolute structure with light atoms. You have to have at least phosphorus or heavier atom to do absolute configuration with molybdenum radiation. So these are just all little tidbits that you have to do to get it ready for publication. So you click refine again. So at this point, you're finished solving the structure. The last thing you may want to do is, I can show you how to draw pictures. We'll talk about check SIF maybe in another class, but to make the naming of the atoms, what you can do is if you come down to mode, naming, start from 1, you do this for each atom type. So you click on this one, name it N1, N2, and then for carbon, you go down again, naming C1, C2, C3, 4, and 5. Then, of course, you have to refine each time. So just a few interesting things about the structure. Here, this electron density peak shown here is in relation to the lone pair on this nitrogen. So remember, this is a sp2 nitrogen, so it has 2 bonds and a lone pair. And so this electron density peak is relating to the lone pair located on this nitrogen atom. These other electron density peaks correlate to the pi cloud in the aromatic ring. So that's pretty cool that you can see this in a crystal structure. Another thing is you can look at the intermolecular forces. So what you would do is, if you want to see hydrogen bonding, you go to the hydrogen, you click bang, explore, and you can see whether it's going to be hydrogen bonding. So this hydrogen here, hydrogen bonds to another aminopyridine as well. So that's something you can look at. So this is the hydrogen bonded chain in aminopyridine. So this other hydrogen, though, is not involved in hydrogen bonding. So only one hydrogen bonds to the nitrogen, and you get this extended hydrogen bond chain. And if you just go bang, you can see its distance is 2.111. It's a fairly strong hydrogen bond. Now, if you type pack, it gives you the packing diagram, and if you type MATR1, it looks down the A axis. MATR2 looks down the B, and MATR3 looks down the C axis. So these are all different ways you can get different pictures of your crystal structure. And whenever you're ready to get a picture, what you do is you go to draw, and I usually use bitmap images, and you click go, and it'll make a JPEG, for example, of this picture. So then you can use it in your crystallographic report. And since it's a packing diagram, it's going to take a little time. So what I'm going to do at this point is I'm going to start fresh again, go through it again, and then I'll take questions. Let's see if it'll. I shouldn't have done packing. Oh well. So while it's doing that, let me do this again. Okay. So again, what you do is you go to open. You open the INS. So if you click on the solve arrow, you select your appropriate program. Most of the time you'll do shell XT. The method is default. If you think there might be a different space group, you can click suggest space group. And it still, OLEX comes back with P212121, and from the data collection, we came back with P212121. So space group is good. So then once you're ready, you click solve. It's going to go through shell XT. Is going to solve the initial model, assign the appropriate atom types. The second step is to double check and make sure all atom types are correct. So whatever's a carbon is a carbon, whatever's a nitrogen is a nitrogen. Then we go to the refine arrow. Make sure the program is shell XL. Cycles, typically I set this to 5 or 6. The fewer you set it to, the more times you may have to do it for the model to converge. Peaks is something that you can go up to 99 peaks, but if you feel that you have most of your non-hydrogen atoms assigned, you don't have to put a very big number. You can put like 10 if you want. Make sure this is set to ACTA, so it creates the crystal information file. You click refine. So now you see that the electron density peaks left correlate to hydrogen atoms. So there's a peak here, here, off the carbons and off this nitrogen. So that's good. We've labeled all the non-hydrogen atoms. We've converged. Our shift is close to 0. That's good. Now you'll notice that this is isotropic thermal parameters, where we treat every atom as a sphere. The next step is to treat atoms as ellipsoids. You come up here to model. Now we're going to do anisotropic for all. It automatically refines it. And this is the point where you should see a big drop in the R because you're going to a better modeling of the thermal parameters. So now our R is gone down. We're getting better. Now here the formula has an orange circle. You can click on it. It'll update it. So again, we've solved the initial model. We've correctly identified all non-hydrogen atom types. We've done anisotropic modeling of the atoms. The next thing is to do the hydrogen atoms. So you can click add hydrogen here, which automatically refines, or you can go to tools under hydrogen atoms, click add hydrogens, and then you'll have to refine separately. So the one under work refines automatically. So if I click add hydrogens, it adds the hydrogens and now it's refining their positions. Now you'll notice here that these hydrogens don't necessarily correlate to the corresponding electron density peak. So let me refine it one more time. So you'll see again that these calculated hydrogens don't correlate to the electron density where the hydrogens should be. So you can delete these two hydrogens. You can go to tools and we can try one more thing. We can click on this one. And now if we put these two, oh, we can't, it's for carbon. If we go to, add hydrogens here and see if this does any better job at modeling the hydrogen atom. So we click refine. It's still not doing a good job. So we're going to remove these now. And we're going to use the electron density map to assign the hydrogen atom position. So you click on them, left click, then right click, type hydrogens, refine. Now it's okay to assign atoms on, or hydrogen atoms on nitrogen and oxygen atoms using electron density maps because typically those gives you better hydrogen bonding distances than if you were to place them on calculated positions. So this does it. Now we've assigned the correct electron density. We right click or left click on both of them, right click, and we set UISO to 1.2 for the hydrogens. Click refine. Okay. So now we've assigned all the atoms, including the hydrogens, so we can minimize the number of peaks. We'll put it at 3. Alrighty. And so you can roll your mouse down, the little button, it gets rid of the Q peaks. If you roll them up, they reemerge. Now the next few things are more technical things. So you can go to info, check the bad reflections. If there's one that needs to be omitted, it'll say omit in red here. You click on it, it'll omit. Now again, this is molybdenum radiation that we collected. So we can, the minimum amount of 2 theta we need is 50, but 55 is a good default. So we come to edit instructions. We type the command omit -355, and this will omit all data above 55 degrees 2 theta. And this will help better refinement of your model. Because again, the high 2 theta data is very weak, sometimes not very good data. So now we've gone to 3.8%, 11.8%. We can update the formula. The last thing we need to do is the weighting parameters. So we click on that. that's going to adjust our goof and weighted R2. The first one, as you decrease it, the first weighting parameter is going to decrease R2, but goof is going to increase a little bit. The second weighting parameter, as you increase it, is going to decrease the goof. So there has to be a balance between the two. I like to call them fudge factors. So then we click refine. Now your goof needs to be around 1 to 1.1. It shouldn't be above 1.1, then it gets a light green. So you wanted a dark green color. Then we click the weighting parameters again, hit refine. Now the shift is perfect. All the atoms are good. Our goof is good. Weighting parameters are fine. If we click on report, here's where you're going to enter information if it's not entered about the fraction. So it's 98 Kelvin. You just import these or input them by hand. The crystal information. So again, the color of the crystal, the size of the crystal, the shape. And this is usually in one of the files that you get from the machine. The crystallographer will measure the crystal for you. And this was mounted. Again, this is all this information that you'll get from the crystallographer about the experiment. You hit refine. And since it thinks it's in a non-centrosymmetric space group, it's going to determine absolute structure configuration. Again, with molybdenum radiation, you need an atom heavier than phosphorus to determine absolute configuration from anomalous dispersion. Since we don't have one, we just put not applicable. We hit refine. And now you're pretty much finished. The last thing, and we'll end with this, is you'll have to come down here and you have to go to your check SIF. Now, if this button doesn't work on OLEX, you can always go on Google and put in check SIF. And this is where you're going to upload your SIF file, and it's going to check it for any errors. So if I click on this, and typically for this to work, you have to put where it says HKL/res, you put it as exclude. And now we click that. It's going to send the SIF file, the crystal information file, to the check SIF to check it for any errors. Hopefully it works on this. It's kind of 50-50. Let me see if it'll work. If not, we'll go to the website and then we'll finish with that. Sometimes it works through here, sometimes it doesn't. So let me stop the share here, or pause it, stop it. Let me bring up the check SIF real quick. So again, all I did was Google check SIF. And it's literally the first hit. You click this one, IUCR check SIF. You go to browse, you're going to upload the SIF file, so you got to find out where you put it. Click on the SIF file, click open. You can either have it output as HTML or PDF. Then you're going to upload what's called the FCF file. So you browse. It's in the same folder. Now you see it's .fcf, the structure factor file, and you upload. And so as long as you don't get any A or B errors, your structure is fine. You can move it on to publication. Now these A errors here, excuse me, my bad. These A and B errors here, they have to do with getting information from a file. So these are not anything too major. These are in actually the P4P file or the crystalclear.cif file. So these are something that can be taken care of very easily. So as long as you don't have any A and B errors and no significant C errors, then your structure is good. You can now get it ready for publication as well. So on that note, we'll stop and I'll take any questions.